DuckDB under the hood, Module 12, Real-World Tuning. Same query, same data, same engine. Two very different runtimes. A simple aggregate over 3 million rows of yellow taxi trip data finishes in tens of milliseconds when the Parquet file lives on local disk. Point that same query at the same Parquet file served over an HTTPS URL, and now it takes seconds. That gap, from milliseconds to seconds, is not a bug. It is the network arriving as a new bottleneck. Across the previous 11 modules, you have learned how DuckDB stores, plans, and executes queries. This module turns that knowledge into a workflow. By the end, you will be able to look at any slow query, run 2 commands, and tell exactly which lever to pull. DuckDB under the hood, Module 12, Real-World Tuning. Parquet is the file format that makes all of this possible. It groups rows into row groups, then stores each column inside the group contiguously. That is the same shape DuckDB uses for its native storage, which is why these two formats work so well together. When DuckDB reads a Parquet file, it reads only the columns the query touches, no whole file decompression. Each column chunk also carries min and max statistics, the same zone map pruning you saw in Module 7. And the row group index lives in a small footer at the end of the file, so the engine can plan the entire scan after a single small read, columnar storage that travels. That is the property that makes Parquet plus a network connection actually work. The httpfs extension is what unlocks remote Parquet. One install, one load, and any read Parquet call now accepts an HTTPS URL, an S3 path, or a Google Cloud Storage path. Watch what the engine does. It fetches the small footer first, and that gives it the row group index. Then it plans the scan and issues range requests for only the column chunks the query needs. The chunks that fall outside the filter or that belong to columns the query does not touch, never cross the network at all. That is what this animation shows. The cloud holds 5 column chunks. The footer flies down first. Then only the relevant chunks, colored, travel to the engine. The pruned chunks stay in the cloud. Network latency replaces disk seek, and every byte you do not request is a round trip you do not pay. When a query is slow, you reach for 3 commands. First, explain. It shows the plan without running it. Use it to confirm the filter has been pushed into the scan, that you are projecting only the columns you want, and that the join order looks reasonable. Second, explain analyze. It runs the query and reports actual row counts and time per operator. This is where the wall clock truth lives. Third, pragma enable profiling. Switch it to JSON mode and you get a machine-readable profile dump you can diff between runs. 2 more knobs round out the diagnostic kit. The DuckDB memory function shows what the buffer pool is currently holding, and set memory limit and set threads pin the test environment so the symptom you saw on production reproduces locally. These 5 tools are all you need to find the bottleneck. Once you have the diagnostic output in front of you, the audit is 6 questions in order. First, are you reading only the columns you need? No select star. Second, are filters pushed into the scan? The filter operator should appear below the table scan, not above it. Third, are zone maps helping? Order your data by the columns you filter on, and the engine will skip whole row groups. Fourth, where are the pipeline breakers? Every breaker is a memory pressure point. If the query is spilling, the breaker that owns the spill is your culprit. Fifth, is the optimizer choosing the right join order? Module 11 covered this. Refresh statistics first. Reorder manually only as a last resort. Sixth, is the bottleneck CPU, memory, or network? The profile says where the time really goes. 6 questions. Apply them in order. Most slow queries fail at one of the first 3. Let us set up the workspace. We install httpfs and load httpfs. That is the one-time setup that lets DuckDB read remote URLs. Then we attach the TPCH scale factor 1 database and switch to it. Now the trick. Instead of downloading a remote Parquet file, we export a slice of the orders table, 1 million rows, to a local Parquet file. That gives us the same file format we would read over the network, on local disk, so the rest of this walkthrough runs offline. The same diagnostic workflow applies either way. We set explain output to physical only, same trick from Module 9, and run explain on a simple aggregate over the Parquet file using read Parquet. The bottom node is a Parquet scan. The data lives in a file on disk, not in a DuckDB table, yet it shows up as just another scan operator. Right above it is the aggregation. 2 operators, 1 pipeline. Same pipeline shape you would see if the data lived in a native DuckDB table, which is the whole point. Once read, Parquet appears in the plan. Every other concept from the previous modules applies. First audit question. Are you reading only the columns you need? Let me run explain analyze both ways. Select star reads every column. The Parquet scan reports the wall clock for reading all 9 columns of orders, every byte range in the file for every row group that passes the filter. Same query, 2 columns. The Parquet scan now reads only the byte ranges for O order key and O total price. Every other column chunk is skipped at the file layer. No bytes are read, not even cached. The wall clock collapses. On wide tables, this is the first lever to pull. Always name the columns you need. Second audit question. Is the filter pushed into the scan? We run explain on the same query. The Parquet scan node now has the filter listed as part of its predicate, not as a separate operator above it. That is filter pushdown. The projection above the scan only carries the 2 columns the query asked for. Projection, pruning, and filter pushdown both fire here on the same scan. When you see the filter sitting below the table scan, you know the engine is rejecting non-matching rows at read time before the rows ever leave the storage layer. Combined with zone map pruning, this can mean entire row groups never get read. Same query twice, once at full resources, once at 512 MB, and 2 threads. Watch the profile shift. The scan reads O order priority from the Parquet file, 1 column filtered through the row groups. The group by aggregates into 5 buckets. O order priority has 5 distinct values. DuckDB uses a hash group by here. At full memory, the hash table fits comfortably. At the top, order by sorts the 5 result rows by count descending. Trivial cost on 5 rows. Same plan shape, but now look at the per operator timing. The scan time is higher. Fewer threads means each core handles more row groups before the scan completes. The aggregation may show a different cost profile under memory pressure. If the hash table had to spill, you will see it in the timing here. This is how you reproduce a production symptom on a laptop. Pin the resources, watch where the profile changes. That is the bottleneck. Your turn. The exercise file has a naive query. Total fare per pickup hour, reading from a remote Parquet URL. It works. It is also slower than it needs to be. Walk the 6-question audit checklist. Apply 1 fix at a time. Projection, pruning, filter, pushdown, then the rest. After each fix, rerun with explain, analyze, and record the wall clock change. Document every fix and its measured effect. The exercise file has the starter query, the worked solution, and a final question. Which fix produced the largest gain and why? Welcome back. Let us verify the capstone. Sum of order total grouped by day with no filter. The Parquet scan reads every row group. There is no filter to push down. The query asks for the whole date range. The aggregate covers the full set, building 1 row per day across the entire history. The wall clock reflects the full scan. The tuned query adds a date range filter. 1/4 of the year, we re-explain analyze. The filter is now pushed into the Parquet scan. Because orders are inserted in date order, the row groups outside the range are skipped via zone map pruning. Entire row groups never get read. The aggregate touches a fraction of the rows compared with the naive query, since the scan already trimmed everything outside the quarter. Same answer set for the matching dates. A fraction of the row groups read. The wall clock drops accordingly. 3 audit checks fired here. Projection pruning, filter pushdown, zone map skipping. And the gain is the product of all 3. One more method worth knowing before we close. You have seen .df throughout this course. It returns the result as a pandas DataFrame. .arrow returns an Apache Arrow table instead. Arrow uses the same columnar layout DuckDB uses internally, so the result moves out with no conversion and no copy. Pass the Arrow table directly to polars with pl.from arrow, or write it straight to Parquet with parrow.parquet.write table. Both libraries read the same memory DuckDB already allocated, 0 extra bytes. The rule .df when the next step expects a data frame. .arrow when you are handing the result to polars, writing to Parquet, or streaming over Arrow flight. For large results, the difference is measurable. Here is what you now know. Storage, columnar layout, row groups, zone maps, and adaptive radix tree indexes. Modules 3, 7, and 8. Memory, the buffer pool, streaming, spilling, and the memory limit knob. Module 4, execution, pipelines, breakers, vectorization, and parallel morsels. Modules 9 and 10, optimization, filter pushdown, projection pruning, join order, and statistics. Module 11, and tuning, the diagnostics workflow that ties it all together. Run, explain, analyze, find the slowest operator, apply 1 fix from the audit checklist, measure, repeat. This was the last module. You have finished the course. Go tune something real.